Hello everyone, this is Monica Lupion and today I will solve the example included in the lecture Boiling and Condensation. The statement of the problem says that 2000 watts of electrical energy are to be dissipated through copper plates measuring 5 centimeters by 10 centimeters by 0.6 centimeters. So we have something like this. And the plates are immersed in water at 390 Kelvin. And the heat is 2000 watts. And the question is, how many plates would you recommend? Okay, so how many plates? And this is 5 centimeter by 10 centimeter by 0.6 centimeter. So first of all, if you remember from the boiling and condensation class, specifically when we talk about boiling, we described different regions during the whole process of boiling, and I highlighted that normally the assumption is for chemical engineers is that we are in region 3, which is the most interesting one from the engineering point of view. So that's what we're doing now. We are going to assume that the process happens within the region 3, which is nucleate boiling. So assuming region 3, which is nucleate boiling. And again, if you remember from the lectures, we define a parameter nucell B, which is equal, or it's a function of the Reynolds and the Prandtl number. And that's equation number 1. And we also define this parameter B in relation to the heat rate per area, the diameter of the bubble over the T minus the T saturation, KL. And this is equation number 2. So let's calculate the equation number 2 because we have the data that we need. And we can also use some of the empirical equations based on the Reynolds and the Prandtl number to calculate as well this Nusselt number, and then we can combine equation 1 and equation 2 to calculate how many plates we need. So let's begin with the determination of the heat transfer per area. Q over the area is equal to 2000 watts that we need to dissipate, and the area in this case we need to consider the two surfaces here on the top and underneath. So the area is equal to 2 times 0.05 meters, 0.1 meters, and this is equal to 0.01 square meter, and this will be for one plate. So we are calculating here what will be the heat rate dissipated in one plate. So the area is 0.01 square meter. This is equal to 200,000 watt square meter. That converting this into the unit that we need for the empirical correlation, this is equal to 63,400 BTU hour per feet square. Okay, so that was a calculation of the heat rate over the area. Now we are going to use some of the empirical equations for calculating this parameter, the nozzle B. And particularly if you take a look to the slides, for the case of considering a plate, we can use the Rose now and show a correlation. And the equation is that Q over area it's equal to the viscosity times the latent heat of vaporization times the gravitational acceleration G times the difference in the density between liquid and vapor times the surface tension raised to 1/2 times the thermal capacity of the liquid times the delta T over the coefficient that we need to adjust this empirical equation, and it's tabulated, times the latent heat of vaporization times the Brand number raised to 1.7, and this is raised to the power of 3. Okay, so we need to look for these values of the property of the fluid properties. We can evaluate those at the temperature of saturation, which is equal to 319 Kelvin, which is 242 Fahrenheit. And we look for water, appendix I in your textbook. If you take a look to the table, we're gonna use as an approximation 250 Fahrenheit, and then we can look in this table for the density of the liquid, which is equal to 58.9 pounds square feet. We can consider that the density of the vapor is very small compared to the density of the liquid. The viscosity is equal to 0.16 times raised to -3 pounds feet per second. The thermal capacity of the liquid is 102 BTU pounds per Fahrenheit. Sorry. Okay, so L it's equal to 0.395 BTU hour feet Fahrenheit. The Brand number of the liquid is equal to 149, and the surface tension over the gravity is equal to 4.04 times 10 raised to a power -3 pounds cubic feet. And finally, the enthalpy related to vaporization or change of phase is equal to 945 BTU pounds. So if we apply now this equation here, if we have everything we need, we have the viscosity, we have the latent heat of vaporization, we have the acceleration, we have the surface tension, we have the thermal capacity, this coefficient here as well. We have the prime number. So we have everything we need. So applying 1R2, we can calculate the value of delta t. So combining equation 1 and equation 2, delta t is equal to 23.4 Fahrenheit, which is quite admissible. So we can assume that one plate is able to absorb this delta T. So one plate will be fine. If this delta T is big, is really big, then depending on the material, but this is copper, but let's say that if we have a delta T over 100 Celsius or Fahrenheit, then we might consider to add one more plate or two more plates. So in that case, depending on the delta P that one plate will be able to absorb, then we will have to divide between the different plates. But as I mentioned, 23 Fahrenheit is something acceptable, so we can consider that just one plate will do fine.